Hey everyone, you know what's really cool? The Nobel Prize in Physics this year went to John Hopfield and Geoffrey Hinton.
Yeah.
And today, we're going to dive into why their work is such a big deal.
It's a pretty remarkable story, actually.
So it's not just some abstract physics research.
Yeah.
It's about how they changed how computers think, how they learn.
Right.
So we're going to try to unpack how physics and artificial neural networks,
Okay.
which everyone uses every day,
Yeah.
how are these two things connected?
Yeah, we think of physics and computer science as separate things, but these two scientists kind of blurred the lines and showed how you can take physics and apply it to build what is now AI.
So let's take a step back before we get into all that.
Okay.
We're talking about the 1940s, the early days of computers.
Yeah.
They were good at crunching numbers, but could they recognize patterns?
Well, that was a different challenge altogether.
Like how our brains do, right?
Exactly. Early computers had a really hard time with things like recognizing faces
Right.
or understanding speech, like things that are easy for us. And the key was to move beyond
Yeah.
just telling the computer every single step it has to do, right? It needed a system that could learn from data,
Okay.
adapt, and make decisions based on patterns, just like our brains do.
So how do they even begin to do that? Our brains are so complex.
Right. Well, this is where things get interesting. John Hopfield, he's a really big name in biological physics. He kind of came onto the scene and he had this amazing insight.
What was it?
He realized that he could take his knowledge of how things interact in the physical world, like magnets,
Okay.
and applied it to understanding how the brain might work.
That's really cool, using physics to understand the brain.
Mm-hmm.
So how did he translate those concepts into something that computers could use?
So in 1982, he came up with this model for an artificial neural network.
Okay.
And imagine this. You have a network of friends, and each friend is a node.
Right.
And they're connected by the strength of their friendship, that's the weights. And these nodes, they're like simplified neurons, and they pass information back and forth based on the strength of those connections.
Oh, so stronger connection means more influence.
Exactly, yeah.
But where's the physics in this?
So, get this. The math behind his model was very similar to equations that describe magnets.
Wow, Frilo.
So it was like, hey, maybe the same rules that govern how magnets work could be applied to how neurons learn and store information.
Incredible. So he was modeling the brain, but using ideas from a completely different area of physics. So how does this network actually learn something?
Okay, so imagine this network of friends is learning a new dance move.
Right?
As they practice, the connections between them, those weights they change, getting stronger or weaker based on how well they're coordinating.
So it's like they're practicing. The more in sync they get, the stronger those connections are.
Exactly, and that's how the network learns.
So it's like muscle memory for a network.
Yeah.
But can it fix itself if it makes a mistake?
Oh, absolutely. Think about it like a misspelled word popping into your head. And then you quickly realize how to spell it correctly. So the network is kind of drawn toward these stable states.
Okay.
We can visualize these as energy valleys in this landscape of learning. It's always trying to settle into the lowest energy state, which is the most accurate.
I love that visual of like finding a comfy spot in an energy landscape. But wait, there was another person involved, Geoffrey Hinton. Where does he fit in?
So Hinton comes in right after Hopfield's work,
Yeah.
but he adds a bit of a twist. See, Hopfield's model, it was deterministic,
Okay.
always predictable. Hinton, though, he introduces probability and fuzziness with a model called the Boltzmann machine.
Okay, he's adding a bit more randomness to the mix. Why?
Okay, so think about it like this. You're trying to learn the style of a painter.
Oh.
You don't just want to copy exactly what they do.
Right.
You want to understand their style so you can create something new that captures the same feeling. So the Boltzmann machine, by using probability,
Okay.
it could figure out the underlying patterns and structures, so it could generate new outputs that were in the same style, not just copies of what it had seen before.
So it's like learning the rules of grammar instead of just memorizing specific sentences.
Exactly.
That's really cool. But I'm guessing there must have been challenges. This Boltzmann machine seems like it would need a ton of computing power.
Oh, you're right. While it was a huge leap forward conceptually, it was really difficult to implement practically because it needed so much computing power.
Yeah, that makes sense.
But this was just the start for Hinton. He went on to develop techniques that made these types of networks far more powerful and efficient, which set the stage for the deep learning revolution.
Well, now I'm really intrigued. We'll have to hear more about that in part 2 of our deep dive.
Sounds good. So before we get into what Hinton did later,
Okay.
It's important to remember that his work, like Hopfield's,
Yeah.
was really rooted in physics.
Okay.
He wasn't just playing around with algorithms.
Yeah.
He was looking at how to use ideas from physics
Yeah.
to build better learning machines.
That's really cool.
Yeah.
So he had these Boltzmann machines, which were really hard to use.
Yeah.
How did he make them practical?
He did something really smart.
What was that?
He streamlined the Boltzmann machine
Okay.
and made a more efficient version
Okay.
called a restricted Boltzmann machine, or RBM.
RBM. Got it. So it's like he took a big, powerful engine and made it more fuel efficient.
Exactly.
Okay, I get that. By restricting some of the connections, he made it easier to train.
Yeah.
But how did that lead to the whole deep learning thing we hear so much about?
Okay, so imagine you're building a skyscraper.
Okay.
The more floors you add,
Yeah.
the more complicated it gets.
Right.
Same with neural networks. Deeper networks with lots of layers can learn much more complex patterns.
Okay.
But they were hard to train, even with the RBM.
So it's like you're trying to teach a dog a really hard trick all at once.
Yeah, kind of. Too much at once.
Yeah. So how did they get around that?
Two big things came into play: backpropagation
Okay.
and pre-training. Backpropagation, it's like a feedback loop
Okay.
that helps the network adjust those weights, those connections, to get better.
Okay, so it's like a coach giving a team feedback after a game.
Yeah, exactly.
They adjust their strategy to play better.
Yeah.
Makes sense. What about pre-training? How did that help?
So pre-training, well, that's about breaking down a complex task into smaller steps.
Okay.
Instead of training the whole deep network all at once, he trained each layer separately using those RBMs we talked about.
Ah, so it's like you're teaching the dog the hard trick by teaching them easier commands first.
Exactly.
And then you build it up.
Got it.
Okay, so all of this computer science stuff won a physics prize. Why?
That's the interesting part.
Yeah.
It shows how these two fields are connected. Hopfield showed how physics could help us understand the brain, and Hinton took that idea and ran with it,
Right.
developing powerful techniques,
Yeah.
drawing on his knowledge of physics all along the way.
So it's like they built a bridge between the theory of physics and real applications in computers, showing how these fields can work together.
Yeah, exactly.
That's really cool. But most people listening probably aren't physicists or computer scientists.
Mhm.
How does all of this affect their lives?
Think about the technology you use every day. Image recognition on your phone, personalized recommendations, voice assistants. They all use deep learning. And that wouldn't exist without the work of Hopfield and Hinton.
So they've changed the way we interact with tech.
Yeah.
That's pretty amazing. We went from equations inspired by magnets to algorithms in our smartphones.
Right.
It shows the power of scientific curiosity and collaboration.
Right.
But wait, there's more, right?
Yeah.
These artificial neural networks, they're not just in our phone.
Oh, yeah. It's way bigger than that. These advancements are revolutionizing all sorts of research, especially in physics.
Physics is getting help from AI. That's interesting.
Yeah. So for one, they're helping physicists design new materials with really cool properties. Like imagine super efficient solar panels.
Yes.
That can capture way more energy from the sun, right?
To help us fight climate change?
Exactly. That's just one example.
So physics inspired AI, and now AI is helping us solve big problems like climate change.
Right.
What else can these networks do?
Well, they're being used to make better climate models too, so we
Right.
can better understand the future of our planet.
Okay.
But it goes even deeper than that.
Deep, you mean like literally deeper into the secrets of the universe?
Exactly. ANNs are being used with the Large Hadron Collider
Really?
to help physicists uncover the secrets of the universe.
Hold on. That machine smashes atoms together to recreate the Big Bang.
Yeah.
And AI is involved.
Pretty much. They're sifting through tons of data to find those particles that help us understand how everything works.
That's amazing. It's like having a new way to see the universe.
Yeah. And they're even being used to map the Milky Way using neutrinos.
Neutrinos. Those things that can pass through almost anything.
Yeah, those ones.
Wow, that's incredible. Okay, before we get too lost in space, there's one more thing I have to ask about.
Yeah.
AlphaFold.
Okay.
I've heard about it, but I don't really get what it does.
So AlphaFold, this is where Hinton's work comes full circle, back to biology and even our own existence.
Okay.
It can predict the 3D structure of proteins really, really well.
Okay, remind me why proteins are important. It's been a while since high school biology.
So proteins are like the building blocks of life.
Okay.
They do almost everything in our bodies, from digesting food to fighting infections, even thinking and feeling.
Wow.
And their 3D structure, that's really important to how they work.
So if we know the shape, we know how it works.
Yeah.
And maybe we can even make drugs that target it.
Exactly. AlphaFold is changing how we discover new drugs and research diseases. It's helping us understand how proteins fold and interact,
Okay.
which could lead to new treatments for diseases we thought were incurable.
Wow, that's amazing. So we started with Hopfield, using physics to understand neural networks.
Yeah.
Then Hinton changed how we train those networks. And now it's leading to breakthroughs in materials, space, and even medicine.
Right. It's a really great story of how ideas can have huge impacts in the real world.
Yeah, it is. So we've gone from those first neural networks to the amazing things deep learning can do today. But what's next? Where do we go from here? We'll tackle that question and more when we come back for the final part of our deep dive. Welcome back. So we've talked about a lot, those early neural networks and the amazing things deep learning can do today. But with any new powerful tech, what about the future?
Yeah, you're right. All the things we've talked about, from Hopfield's early models to Hinton's deep learning revolution,
Really?
they've opened up a ton of possibilities.
Yeah.
But they also raise some really important questions about what comes next. Where do we go from here?
It feels like a whole new era of science. We see these artificial neural networks solving problems that used to seem impossible.
Right.
From making new materials to figuring out the secrets of the universe. But what are the next big things?
Well, one really exciting area is making even smarter AI. Imagine networks that can not only learn from data,
Yeah?
but can also think and plan and even be creative like humans.
Okay, that sounds pretty sci-fi. But if we can do that, create AI that can really think, isn't that a bit scary? What about control? Unintended consequences.
Absolutely. As AI gets more powerful, we have to think about what that means ethically. We have to make sure these tools are used for good and that we're careful about potential risks.
So it's not just about the science itself, but how we used it. It's like we're at a crossroads, right?
Exactly. The choices we make now will determine if these technologies help us solve big problems or create new ones. It's something everyone needs to be talking about.
Yeah, that's a lot to think about. But that's what's so interesting about this whole topic is not just the tech stuff, but how it affects all of us.
Absolutely. And I hope that what we talked about today
Yeah.
not only gave you an idea of how powerful these networks are, but also got you thinking about the future of AI and what it means for our world.
Well said. And to everyone listening, keep thinking about these things, stay curious, and we'll see you on the next deep dive where we'll explore some other cool area of science and tech.